Let's start today with a general structure of any instruction. As we already seen, it starts with some prefixes, then opcode, then mod RM byte, scale index base, of all these fields, only opcode is mandatory one. For example, instruction like nope 90 hex is just an opcode byte and nothing more. Or perhaps near return has a similar code consisting only of opcode without any additional information. Previous time we also analyzed some instructions that use mod RM and SIG bytes. Displacement is only present when mod is 1 or 2. As you might recall, mod equal to 0 is memory operand without displacement, and mod equal to 3 is a register operand, and there is no memory addressing then at all. There are also so-called unary groups, groups of instructions that take only a single operand. So then this part of mod RM refers to that single operand, and register, what is normally register field in this byte, is an index of an instruction within a group. Now there is something interesting that happens when we move on to 64-bit world. This is a row that has increment instruction originally in old CPUs on old modes, legacy modes, reused for a REX prefix in 64-bit architecture. And also this another row, this was decrease register. This is another example where octal system makes a bit of sense. We have two ranges here. And in octal system, this would simply be 10x, 11x, octal. Is that right? Yes. And x is again a single octal digit that encodes a single register. So in long mode of 64-bit CPUs, these codes have been reused for REX prefix. So it is no longer possible to encode such instruction this way. But there is still another way. Here we have increment and decrement as instruction groups as regular single operand instructions. The ones that have a code of instruction in R and a single operand encoded normally as memory or register. When mod is free, then this is register, otherwise this is memory. Therefore, even when we get rid of this row of encodings, it is still possible to encode the same increment instruction, but with 2 bytes instead of just 1, because this encoding uses just a single byte for instruction code, and the other encoding uses opcode and modern byte to encode a single operand. Now let's take a look at rex prefix. This entire range is taken by rex prefix, so the high nibble is always 4x and the low nibble are 4 bits that encode 4 different things. Oh, this is nicely shown on this diagram here. If we present mod RM byte in this form, all 8 bits, then rex prefix, then this R is an additional bit for this field, and this B is an additional bit for this field. But also, if we have when M field is 4, then we have another byte, scale index base. Well, we might use X for index in this case, because this X in rex is then 4th bit for this field. And again, B goes to extend this one to 4 bits, and R goes to extend this one to 4 bits. So with rex prefix, where we had octal system to encode 8 possible registers, with rex we have 16 possible registers, so we need 4 bits to encode every one of them. But because of the legacy of Intel encodings, we had to split these bits, and additional bits are just here in rex prefix. And of course, because rex prefix in legacy modes, in 32-bit mode and 16-bit mode, it still means the original increment decrement instruction. So it is not possible to have such prefix in the older modes, and therefore it is not possible to access the additional new 8 registers, only the old ones. And then when we move to AVX, we again have this RXB as in rex prefix within VEX prefix. And the choice was that since we were not able to use new registers, more registers than the basic 8 in modes other than 64-bit long mode, then VEX design was such that it should no longer be possible to access such registers in legacy modes, even if VEX can be used in old modes. VEX prefixes use codes of LES and LDS instructions. These instructions required memory operand. Encoding them with register operand was not allowed. It was invalid instruction. So it was possible to reuse this code even in legacy modes, even in 16-bit mode and 32-bit mode. For this reason, VEX is still possible to have in 32-bit mode. And it is possible to use AVX instructions in 32-bit mode. However, VEX, the byte that follows VEX, on old CPU would be interpreted as mother M, and to distinguish such VEX from LES instruction, mod has to be 2-bit set, value of 3, so that it would choose register operand and not memory operand. Therefore, for both these prefixes, the second byte needs to have 2 highest bits set when we are not in the long mode, because this then indicates that this would be a register operand and this would be invalid instructions, so we can reuse it for VEX prefix. In long mode this is no longer a problem, because in long mode there is no LDS or LES instruction at all. These opcodes are completely free in long mode, so they were available to reuse for VEX. So the brilliant idea they had was to put this RX up here and then invert them. So where in Rex R was 1, now in VEX R must be 0 and vice versa. And in 32-bit mode, in legacy mode, we are limited to use only basic 8 registers. We do not have access, by design, we do not have access to additional 8 registers. So R and X and B are going to be 0 normally, as encoded in VEX. And with this inverted encoding in VEX, they are going to be 1s. And this ensures that these two highest bits are 1, 1. So there is no conflict with LES or LDS instructions. In this case, this is R and highest bit of V, additional register, because AVX instructions allow 3 operand instructions, something they also call non-destructive source. As in, you can have 2 source registers and another destination register, and the result of operation does not rewrite any of the source registers. 3 different operands. So to make this work, they also had to invert this entire field. Well, it would be enough to invert just the highest bit, but it would be clunky then, so entire VVVV is inverted. And then there is EVEX. This time we are reusing code that was originally bound instruction. We can find it in the table. Bound is here. This is another instruction that only allowed memory operand. So again, we can use the same trick to make it work in legacy modes too. We just need to ensure that in old modes, 16-bit mode and 32-bit mode, that we use such encoding that this would be bound with register operand which was invalid. So the second byte after 6.2 has RXB in the highest bits. So as long as we also invert them in EVEX too, just like in VEX it was, we are going to have it working just the same way. But what is interesting this time is that AVX 212 introduced even more registers, not just 16 registers, but 32 registers. So to encode an individual register we need 5 bits instead of 4. And for this reason we have bits such as another bit after R higher, and higher bit for V. This might look a bit strange. Why not put this additional V bit here and just have consecutive 5 bits to index a register? But the layout they used here is the same layout as it was in VEX, just extended with new information in third byte. So the third byte is what's new compared to what was in VEX. One exception is the L bit that has been moved in EVEX. Wait, I'm lost. Where was my EVEX? Here. As you can see, there is just a set bit 1 here. And L has been moved here next to extended L. There are now 2 bits that choose the size of vector, because AVEX 512 allows more size of vectors. XMM registers, YMM registers, and ZMM registers. 3 different sizes. And this is what Intel architecture has become. Many fields that need to be encoded as 5-bit values, but the bits are all over the place. The original 3 bits are still in mod_rm or SIB bytes, and the additional 4th and 5th bits are here, but also in various places, all around the place. Alright, do you have any questions? I'm not going to talk long today because my throat does not feel very well at the moment. Yeah, EVEX seems very unpleasant. It is in fact even more unpleasant than it appears to be just looking at this. For example, some bits like this one can mean different things depending on context. And I mean completely different things. When instruction has memory operand, then this bit can mean that operand is broadcasted to fill entire vector. And when the same instruction uses register operand instead of memory, then this bit can mean an additional modifier to how exceptions are handled. This tight packing of information is strange considering that there are still bits that are actually unused here. Perhaps they were reserved for other purposes. How many of them does it fit? And a similar instruction. Oh, I don't even remember all these French names. Round up, right? Not for this one. Oh, yeah. I did rightfully say that I did not remember these names well. You can see that VEX prefix is exactly the same. For both these instructions, the oh sorry, this bit B is set, but it means two completely different things in the two cases. Here it means that this is broadcast, and here it means that this is this rounding mode chosen. Well, I'm using the same settings, so if resolution is worse for you, then perhaps it's bandwidth problem. We can later check in recording. Alright, I'm not good at talking today. So if you don't have any more questions, I'm probably going to wrap up